Hello, my name is Huaigu Tang. My research topic is borehole acoustic full-waveform inversion. I am a PhD student in the group of Singapore Geophysics project in National University of Singapore. I'm also sponsored by Southern University of Science and Technology. This project is constructed by my supervisors Arthur, Elita, and Xing Ding. We also acknowledge Halliburton for sharing field data with us. This research aims at inverting the spatial variations in formation velocities around a borehole from acoustic logging data. At the beginning, I would like to briefly introduce acoustic logging. Acoustic logging is also called sonic logging. It's a principal geophysical technique to measure the elastic wave velocities of formation. The acoustic logging tool is mainly consists of transducers of source and receivers. We follow recording geometry of Halliburton Examiner Sonic Imager, which is an advanced acoustic logging tool. The tool has 4 monopole sources and a pair of dipole sources. In this project, we use only ultra-far monopole source, far monopole source, and lower near monopole source. Monopole means the acoustic waves generated by the source radiate equally in all directions. There are 13 rings of receivers. Each ring consists of 8 evenly distributed receivers. Interval between the rings is ½ foot. During the work, the logging tool will be firstly put into bottom of the well. Then the tool will be lifted up to the surface. In this process, the sources send out acoustic waves to the borehole fluid with an interval of ½ foot. When the acoustic waves travel to the wellbore, the acoustic waves will transform to elastic waves. There will be compressional wave or P wave, shear wave or S wave. S wave are followed by pseudo-Rayleigh wave. There are also Stoney waves. P wave and S wave are body waves. Pseudo-Rayleigh wave and Stoney wave are surface waves. The surface waves only travel along the wellbore. When these body waves and surface waves travel to the position of receivers, they were recorded as acoustic logging data. Further, we can calculate elastic wave velocities of formation from the acoustic logging data. Acoustic logging and seismology are both acoustic methods based on elastodynamic theory. In other words, they all follow elastic wave equations. However, compared to seismic velocity model, which are always 2D slice or even 3D volume, acoustic logs are just 1D curves. Usually, the fluctuations on acoustic logs are interpreted as lithology change in axial direction along borehole. The curve do not have resolution in radial direction away from borehole. However, in many cases, velocities are changing in radial direction of wellbore. For example, when borehole fluid intrudes into the wellbore, the velocities in the flushed zone and the transition zone may decrease because of the fluid substitution. Another example is about stiffness variation or velocity variation around borehole induced by tectonic stress. The traditional methods used for obtaining acoustic logs cannot quantitatively calculate velocity structure like this. Therefore, we propose to apply full-waveform inversion to invert the velocity structures from acoustic logging data. Currently, we are not dealing with 3D problems. By assuming formation is invariant in azimuthal direction, we can deal with a 2.5D problem in a 2D slice. In addition, because source wavelet for the monopole sources are the same, the original near monopole data, far monopole data, and ultra-far monopole data could be realigned to one data set. The recording geometry for the combined data set consists of one source and 39 receivers. Before we talk about full waveform inversion, let's first talk about the conventional method to measure velocity from acoustic logging data. In this schematic, the recording geometry consists of one source and two receivers. If the formation is homogeneous, the repaths of the first arrived waves are all along the wellbore. In this case, the difference between the two repaths equals to the spatial interval of the receivers. Next, we only need to know the time difference between the first arrived wave. The velocity of the formation could be calculated by the spatial interval over the time difference. In the logging industry, people prefer to use slowness, which is just the reciprocal of the velocity. In this slide, the idea is better illustrated by using numerical simulation. A monopole source and an array of receivers are put in the middle of the borehole. The velocity of the borehole fluid is 1,500 meters per second. The P and S wave velocities for the homogeneous formation are also given. Then the propagation of the elastic waves could be simulated by using numerical methods. These fastest waves are P wave. These are S wave, followed by pseudo-Rayleigh waves. These are Stoney waves. When these waves travel to the position of receivers, they were recorded as acoustic logging data. The idea of traditional method to obtain velocity or slowness of the elastic waves is by measuring the slope of the first arrived waves in the data. The standard method to measure slopes of the elastic waves is Semblance. Semblance calculates velocities according to coherence of waveform in selected time window. The bright points on the Semblance panel indicate the slowness of the elastic waves. We see that velocities obtained by Semblance are very accurate when formation is homogeneous. Actually, the acoustic logs are calculated by using Semblance. However, Semblance results could not quantitatively tell velocity variations in radial direction around borehole. In this case, P wave velocity is changing from 2,600 meters per second at wellbore to around 3,000 meters per second at 1 meter away from borehole center. However, Semblance results would only give us a somehow averaged number. This is because when formation is homogeneous, all the repaths of the first arrived waves between the source and the receivers are along the wellbore, and the first arrived travel time curve will be a straight line. However, when formation velocity is changing in radial direction, the penetration depth of the repath will changing with respect to the offset. In this case, the slope of the first arrived travel time curve would also be changing with respect to the offset. Therefore, Hornby proposed to apply ray tracing tomography to obtain P-wave velocity profile around borehole. With the development of computer, we can use not only the travel time of the first arrived waves, but the whole waveform of the data to obtain elastic wave velocities. This technique is called full waveform inversion. Full waveform inversion has potential to obtain velocity model with higher resolution than ray tracing tomography. Full waveform inversion search a velocity model to make the data residue between the synthetic data and the observed data as small as possible. Because the synthetic data and velocity model follows the elastic wave equations, mathematically, the full waveform inversion solves a constrained optimization problem. There are many methods to solve the optimization problem. Here, we use a gradient descent method because it's simple and stable. The gradient descent method finds the velocity model by iteratively searching in the opposite direction of gradient of objective function with respect to the model parameters. To start the inversion process, a starting model M0 is needed. The quality of the starting model is very important for FWI. Later, we will use a simple example to show our strategy to build the starting model. This is the workflow of a gradient descent method. Input of the algorithm is the starting velocity model and the observed data. Gradient is calculated by cross-correlation of the forward wave field and the adjoint wave field. Output of the algorithm is the velocity model updated by using the gradient. The updated model would be the starting model for the next iteration. The full waveform inversion has been developing for seismic velocity model building for a long time. In this project, our contribution is to revise the algorithm from Cartesian coordinates to cylindrical coordinates to make the method suitable for borehole environment. These are the equations in the full waveform inversion algorithm based on cylindrical coordinates. We are not going to talk about the details because of the time limitation. Here, we would like to stress that we are not inverting P and S wave velocities directly, but we update elastic modulars first. Then, either the elastic wave velocities or slowness could be transformed from the elastic modules. We use this simple layered model example to briefly show how full waveform inversion works. Now assume we do not know the true velocity model, and we are going to invert the layered model from the observed data by using the gradient descent method. At first, we built the starting model based on semblance analysis. We use semblance results of near monopole data to estimate velocity near the wellbore. Similarly, we use semblance results of ultra-far monopole data to estimate velocities far from wellbore. The velocities in the middle are interpolated linearly. In this way, a smoothing starting model is obtained. Further, we can calculate gradient based on the starting model and update the velocity model. We see that after 50 iterations, the inverted velocity model is already very close to the true velocity model. We also test the applicability of the full waveform inversion by using field data. The starting model is still built based on semblance analysis. This is the inverted results at number 50 iteration. We see that there is an abnormal low velocity area near wellbore at depths between around 2050 feet to around 2085 feet. The resistivity logs also show that there is resistivity change in radial direction in this area. The decrease in objective function also shows that the data residual between synthetic data and observed data is decreasing with the updating of the velocity model. Therefore, the inverted results is believed reasonable. Finally, we thank Halliburton Company again for sharing the data with us, and thank you for your attention.